Section 2.4, the graph of y equals kx. So this is just a brief introduction into graphing direct variation equations. And these should be fairly straightforward because we've already graphed linear functions, and this is just a simplified linear function essentially. All right, so let's just talk about a few things. So the first definition we come to is slope. The slope of a line through 2 points that have coordinates, let's say x1, y1 and x2, y2, equals y2 minus y1 over x2 minus x1. So this is just your slope formula. And remember, slope is the rise over the run, so the change in the y's over the change in the x's. The theorem here says the graph of the direct variation function y equals kx has a constant slope k. And when I taught direct variation, I mentioned this a couple of times, that the k value is essentially just your slope. The only thing new we're going to talk about here is with the y equals kx, or the direct variation functions, we're going to talk about something called domain and range. So in general, the domain of the function with the equation y equals kx is negative infinity to infinity, or we could just say all real numbers. So what this means is if we were to think in terms of like a coordinate plane, so your x and y axis, and you're to draw a line here. What this means is that this line is essentially going to cover all possible x values going left and right, because that's what the domain talks about. Domain talks about possible x values that will be defined for your graph. And so for linear functions, it's always all real numbers because it can cover any x value possible. And then the range is your possible y values. And so the same thing is true here. So the range is all real numbers or negative infinity to infinity. All right, so this is negative infinity to infinity, meaning that it could cover every possible y value from top to bottom. Just depends on how the graph is drawn. But in reality, unless it's a vertical or a horizontal line, it's going to fall under this suit that all linear functions have a domain of negative infinity to infinity and then a range of negative infinity to infinity. So it's covering all real numbers. So for example 1 and 2, we're starting off really easy here. We're going to talk about what is the slope of the equation y equals 3/5 x. So in this case, we should be able to identify the slope as being our k value or our constant of variation. So it's 3/5. And remember, this tells us that we're going to go 3 up when we go to graph this and 5 to the right from our point that we start from. All right. What is the slope of the line for y equals negative 5x? Well, your slope would be negative 5. So negative 5, and remember that's negative 5 over 1, so you'd be going down 5, and then right 1. So recall that the slope formula is y2 minus y1 over x2 minus x1. And so we're going to use that formula to find the slope between these 2 points. So we've got x1, y1, x2, y2. So using our slope formula, we're going to set this up. Negative 9 minus 7 over 5 minus negative 3. So in this case, negative 9 minus 7, well, that's negative 16. Here we have 5 minus negative 3, so we change the sign because there's 2 negatives there, so that's 5 plus 3, so that's 8. So our slope in this case is negative 2. Question B, same idea. We've got x1, y1, x2, y2. So we're going to set up our slope formula. 2 minus 8 over 6 minus 12. 2 minus 8 is negative 6. 6 minus 12, well, that's negative 6 as well. Negative 6 divided by negative 6 is a positive 1, so your slope is just 1. And if we wanted to write direct variation equations for these, we could. We could say y equals negative 2x. And then y equals 1x, but they didn't ask us to do that, so we just had to find the slope. So in example 2, it asks, what is the slope of a horizontal line? So it's easier if we picture this. So if we take a quick look and we try to picture this, So if this is our x and y axis, and we're talking about a horizontal line, so that would be this line here. Well, in terms of rise or run, it runs forever. It goes left and right, but does it ever rise? So no. So your rise would be 0, but your run could be any number. So let's say it runs forever, so it runs for 2. Well, no matter what you do, because it's never rising, your slope here for a horizontal line is going to equal 0. And then for a vertical line, well, we do the same thing here. We draw our coordinate plane, and then we have this vertical line here. Well, this particular graph grows forever. It rises up and down forever, but it doesn't move left or right. So in reality, we could do like 7 divided by 0 because, I mean, we could use a higher number for the rise, but we don't need to. But when we try to divide this, your calculator tells you error. So for a vertical line, we have to be aware of a couple of things. The slope for a vertical line is undefined because you can't actually calculate it. It's rising so fast, but it's not moving left or right, so you can't actually calculate the slope. So here it says graphs of the equation of the form y equals kx pass through the point 0, 0 when graphed. So for this example, they ask us to graph the following equations. Well, the first equation they give us is y equals negative. So here we're going to graph the equation y equals negative 4x. So the idea here is that we need to make sure that we look at this and it looks like slope-intercept form, but it's missing an intercept piece. Well, all direct variation expressions like this pass through the point 0, 0 or start from a y-intercept of 0. So we're going to put our first point at 0 on the y-axis. Then we're going to apply our slope. Well, negative 4 is really negative 4 over 1. So we're going to move down 4, right 1. So we go down 4, right 1, down 4. Well, we can't go any farther, right 1. Got to estimate where it is. If we want to go backwards, up 4, left 1, up 4, left 1. So now that we have our points, we can go ahead and graph our line. So here we're going to graph y equals negative 4/3 x. So remember, we're going to start from 0 and apply our slope. The negative 4 is the top, the 3 is the bottom. So we're starting from 0. I'm going to go down 4, right 3, down 4, right 3. I'm off the grid a little bit, but that's okay. If I want my back points, I'll go up 4, left 3, up 4, left 3. So this is my graph. Go ahead and take a second and graph C on your own. So pause the video, graph it, and then unpause it to check your answer. So for C, you have a slope of 3/5, and you're starting from 0 again. So you're going up 3 over 5. If you want the additional points the other way, you go down 3, left 5. And then you just connect your points. And this is enough to draw your line. If you want to extend your line, you can. I recommend it, so we'll extend it a little bit here. And there is our line. Keep in mind that all direct variation problems pass through the point 0, 0 in this case, and you have the slope out in front. So your constant variation is your slope, and you're applying your slope like we've always done.